Yes, so I'm David Richards. I'm a UKCRIC Director and Research Strategy on the coordination node, and also the sort of responsible person in terms of EPSRC for the capital grant for the construction of the NIL at Southampton. So it's very good to be able to share where we've got to in terms of the formation, development and building of the National Infrastructure Lab. So that is a slightly less oblique angled view of the NIL from the one that William showed earlier. So it forms part of our Boulderwood campus at the University of Southampton, which we share with Lloyd's Register, making it one of the biggest industry and academic based partnerships in the country. And also it's a campus which has our additional university buildings housing about just under half of the School of Engineering on the campus, the other half being down on the main campus at Highfield. So, and if you just want to run the video, as they say, that should give you a flavour of the campus and its wider setting. I think there's a bit of buffering necessary.
Yeah, I'll keep the sound down because it's not very good earlier.
Right. It's a bit of a fly through, but it looks like it's buffering and a bit juddery. But that's our geotechnical centrifuge, which I'll talk a little bit more about later in the presentation. Very useful for running models and simulations where the scaling can allow us to accelerate time if there are consolidation type processes going on. This is our main geotechnical lab, which is a large open plan space which works extremely well compared to the sort of rather cramped and time expired facilities that were on the main campus. And we have a range of machines and advanced element testing machines. This is a view of our strong floor and various reaction frames, and that's part of the rail laboratory and rail experiments on long-term settlement of ballasted track. We also have very extensive material testing. Again, there'll be some more details of that in the more conventional type of PowerPoint presentations, impact tests, high strain rate testing, very data rich, vast amounts of data, looking at the formation of crack propagation and things like that. And these are just some views of some teaching facilities. So we combine teaching and research and enterprise in all of our facilities, and that's a model that we run across the School of Engineering. And so they are school facilities broadly, supporting all of our programs and research across the disciplines of ship, mech, aero, astro, civil and sound vibration. That's a driver simulation as part of our human factors work, and it's about human perception. And this is our tow tank, which is a building up to the north of the site, 148 meters. Very fast carriage, which can go to about 12 meters per second, which is about Usain Bolt at full tilt. And it's used for performance sports and various other facilities that you would expect in a hydrodynamics laboratory. So this is a flume, mainly for teaching. This is our anechoic wind tunnel, looking at issues around aircraft noise mitigation, and forms a very large group activity. So that's an aerial view of the campus, and the NIL is that, well, we missed it, but anyway, it's the one as you drive in, it's just on the left, and that's our main campus. Okay, thank you, Anne. So Anne's going to just be advancing these. So we opened formally in 2019 with a handover of the building, but with a building as complex as this, we are still really operationalizing the building. And during the course of the build, we were successful in winning a number of capital grants to support the equipment, that some of which you'll see in this presentation, and which also impacted or augmented rather the base build as part of the contract that was bought by the main contractor and as managed by the university. So, as I say, a very complex building. So we've combined a strong floor a geotechnical centrifuge, advanced geotechnical laboratories, all housed in one big building. So that is a complex building by any measure. As I say, we are still equipping it and operationalizing the building so that it can be fully functioning. So we have research teaching laboratory, so geotechnical centrifuge, strong floor, geomechanics lab, and testing and structures laboratory, which is the material testing, and our energy group has an energy laboratory from which they prepare sensors and apparatus for long-term monitoring of large buildings and domestic buildings and looking at energy use. And the view you can see at the top is we have an informal learning space in these and the ground floor as you go in, which facilitates small group presentations or much larger group gatherings. And then up in the lab, the very open plan nature facilitates group projects, group learning, and allows in the current COVID environment very effective distancing. So it's a very efficient setup, and one that we've been very pleased to have with the current restrictions being posed in terms of building access. And if you could push it forward, please. So this is the opening event. So this is the opened up ground floor for the short presentation. So this can be divided up and rearranged furniture that can facilitate small groups. So very much part of the informal learning space, which was a key requirement of the building design to allow but industry, students, researchers to combine and come together, and is a very effective space. Anne? So the geotechnical centrifuge is a 6 meter diameter 130G machine. It can, just to put that into context, one day of testing can represent up to 40 years of a loading process, particularly in terms of the scaling laws that are applied to consolidation events. So that's the movement of water through the ground due to applied loading. And we have a series of large strong boxes that you can see on the right with a plan area which can be at 130G equivalent to the site that is shown in the red box further to the left. So it can represent a very large footprint, and we have multi-axis robotic actuators. We can characterize the soil in our model, and it takes real soil with a real stress strain response and subjects it to loading that will represent what we would get in the field because of the nature of what we are, because we are using a real soil. And within the real soil, you've also got, as I said, the consolidation and groundwater flow mechanisms that are accelerated due to the application of G. So on the right, that is a view of the centrifuge. There's the swinging platform at the extreme right-hand side, that rather triangular looking thing. And that's where the payload goes, the strong box, which contains our soil. And we can configure that soil to represent slopes or retaining walls and cuttings and undertake long-term tests, as well as characterizing the soil. So we've got the actual soil properties from which we can derive mechanisms. If you advance one, please, Anne. So this is an application of geotechnical centrifuge modeling. This was some work that was done some years ago now, actually, but it was at the very start of looking at how we might go about optimizing the stabilization of slopes using piles. And the key problem we were looking at there is what was the optimal pile spacing to both support the slope and also allow arching between the piles to prevent the soil between the piles from just moving through the gap. So that was a series of tests that we undertook in the centrifuge. 1:60 scale. We've got 3 model piles with the central pile you can see with the black cap on it being instrumented for bending moments, and the slope was preformed, placed in a centrifuge, spun up to G, everything allowed to consolidate, and then the groundwater was allowed to rise, therefore reducing effective stress and inducing a slope movement. And then we were measuring the bending moments as the soil was being, movement was being resisted by the piles, embedded and towed into material that wasn't moving. And you can see the black dots that have been placed onto the side and onto the surface. We were using an early image processing software and image processing techniques to determine the strain measurement of the surface to try and pick up the arching mechanism through those two gaps with those three piles. The material that we tend to use is specified kaolin. It's highly controlled. We understand its properties, and it is fairly permeable, and that allows the water to flow through it quite readily, even though it is fine grained sufficiently to be classified as a clay. So the overall mechanisms associated with that were then very informative in then some field work. So, Anne, if we could move on. So this was applied then, the knowledge from those series of tests, which were published in a Transport Research Lab publication and co-sponsored by the TR Transport Research Labs, on the London Underground lines and the a number of locations actually. There's been some field trials of actually putting in piles to stabilize the slope, and then some of those piles being highly instrumented to continue and into the long term measure the bending moments as they start to take up the load and resist the slope movements. And also we had inclinometers in between those piles to pick up any soil movements directly through the use of an inclinometer slope measurement system. And we've got a number of these sites around the UK, and the mechanisms and the spacing from the geotechnical centrifuge modelling was extremely influential in determining the layout of these full-scale. Some of them are both trials, and actually some of them were beyond trials. They are actually primary slope stabilization processes that have been employed to extend the life of the infrastructure and reduce the costs of the long-term slope stability issues that have affected quite a significant sections of our above ground rail systems. If you could move on, please. So these are some shots of the piles being installed on the left-hand side. You can see the instruments coming out of the piles all being cast in place. So a site like this is quite an aggressive environment, as you can see. So our instrumentation has to withstand the problems of that aggressive environment and survive through the construction process with those rather fragile and vulnerable cables that you can see. We've got a lot of experience in that type of field work, and we employ data loggers that are taking data at very frequent intervals, and that richness of data allows us to be able to really analyze and further undertake modeling of the field trial, which combines with the earlier scoping trials in the centrifuge to give us a much better understanding of the mechanisms, and then the optimization and engineering interventions that we need to undertake to stabilize these type of slope problems. So on the right hand side you can see that there's been some earthworks to just even out the slope to protect the piles. This is the trial at Hildenborough with the final slope geometry, and I believe it's still pulling in data and giving us long-term information about the performance of pile stabilized slope initiatives. If you'd like to go forward, please, Anne. And the rainfall and groundwater levels and other things that are being measured on these slope sites all combine to give us a very long-term accurate record of the climatic events, linking that to slope stability. Another example of our field trials is a more recent set of trials looking at overhead line equipment foundations, and on the back of the Great Western Electrification Programme, which overran and also experienced severe cost escalation to do with the installation of both the piles and other factors. We undertook some testing to determine the efficacy of an empirical 1950s design methodology with lump factors of safety, which had been derived from many hundreds of full-scale tests to create this empirical model, and then rolled out across the UK and the continent. So we've got many millions of OLE foundation years of experience from all the hundreds of thousands of foundations that are out there designed to this methodology. But the application of new design methods, and then in particular serviceability being applied to the deflection calculations of these foundations, meant that these foundations became quite long, the Great Western, and for various other reasons, the scale of the foundations also had much higher loading because of the robustness, additional robustness that was applied due to the, I think, primarily interoperability requirements of overhead line electrification schemes. And so everything sort of just expanded. Then the size and depth of the foundations became so large that it was very difficult to actually get the foundations in the short track possession periods that existed. So we undertook some field testing to provide some evidence of the much higher loads using the OLEMI design methodology. And we applied it in a real setting where you've got all the imperfections of the embankment slope. And on the right-hand side, you can see that we were also monitoring the slope with a set of electro levels that were all networked to provide us with an early indication of any problems associated with both the installation and the testing of the pile foundation on the side of the slope directly. We're also measuring the deflections. We were subjecting them to the very high loads. So on the right-hand side, you can see the kentlage that's being hung off that beam, which is applying a bending moment at ground level on the main foundation. And then we had an additional foundation and column setup on the left-hand side, which was connected to a jacking system, which allowed us to then input the additional load due to wind, the 1 in 3, the 1 in 50 wind, and then to take the foundation to full failure. So this represents an extra large twin track cantilever in terms of the overturning moment, which is a very significant amount of kentlage you can see. And then the horizontal strand you can see at the top was a jacking system that allowed us to increase the working loads to represent the overturning moment induced by the wind. If you want to move forward, please, Anne. So these are just some results. We did the extra large twin track cantilever, which was presented in terms of the OLEMI design load against the lateral head displacement as measured directly on site. We also measured the deflected profile of the foundations, the steel pile foundations as well, very, very accurately. And we came up with a system that allowed us to determine the lateral displacement at the top of the head from a fixed set of inclinometers that were extended beyond the toe of the pile, so that it was fixed, and then we could sum up the displacements of the sensitized elements all the way up the inclinometer. We were also looking at twin track cantilever, which is probably the more common, and the single track cantilever, different structures which are less loaded than the XLTTC, and we were getting 2.2 to 2.5 or thereabouts OLEMI design load factors, which was strongly indicating that the lump factor of safety on the OLEMI empirical design method was sufficient, that we would have confidence that these much higher loads and using smaller diameter steel piles, which are much easier to install, providing us with confidence that those foundations would prove adequate for supporting the loads, and extended the OLEMI design method into those much higher loads and smaller foundations. So much so that we were able to advocate the new design specification and support the development of that for Network Rail as part of future electrification programs going forward, which will save considerably in terms of costs and time for the installation of those piles. If you want to move on, please, Anne. So this is the large structures testing laboratory. This is a sort of 360 wraparound. It takes a bit of getting used to. So this is from a few months ago, and there's been a lot more placed on the strong floor. Strong floor is a 30 metre by 50 metre large hall for structures and substructure testing. And the yellow and orange steelwork that you can see, those are parts of the reaction frames which are bolted down onto the strong floor, which forms part of the closed reaction system, from which large hydraulic actuators are then placed in the frame and between the frame and the element that's being tested, and can subject large structural elements to large repeated loads in the more traditional structural testing sense, but also the floor houses a number of rigs that supports the long-term ballast behaviour and track ballast work that's being undertaken in support of the rail research, which takes place on the strong floor as well. So it's in 3 sections. So right in the middle of the picture, you can see a channel going down through the centre, and then like a T shape. Those represent 2 independent parts of the floor, which can be coupled, and then the floor in the foreground is a larger section, half of the floor, that extends back to the door, and so we can have experiments going on independently, or if you've got large experiments, they will straddle 2 parts of the floor, or even 3 parts of the floor, and will act in uniform. So everything can be blacked out, and we can use white light source and various other advanced methods of measuring the performance of the structural elements being subjected to testing. If you move forward, please, Anne. So these are some views from some more recently set up reaction frames that have just come onto the floor. This is part of a Structures 2025 research project, EPSRC funded, looking at hybrid testing and modelling using various advanced imaging and loading techniques, and we're just now equipping and erecting these onto the strong floor in support of the tests that are looking at large wind turbine blades, but only a section of those blades, which could then be used to understand the whole structure through advanced numerical modelling of the actual tested elements that are placed in these reaction frames. So an awful lot of equipment has been brought onto the strong floor through this process of winning large grants and being supported as part of the UKCRIC, which is a rail research activity that goes on the strong floor. The strong floor is supported by 4 very large pumps, which can, when we've got 2 pumps that are just being energised now, which came in during the course of the build, and which will bring the total capacity of oil being moved through the high pressure hydraulic system up to 1,000 litres per minute, which will support all the actuators and a range of testing that will be going on simultaneously. So it's a very large floor. It's got a lot of testing apparatus already on there, but we're managing in a way that we can get people on and off pretty quickly, as well as, again, continuing to fully operationalize the building by having the additional equipment that was purchased during the course of the base build become installed and operational. Anne, please. So the Geomechanics laboratory is where we do our element testing and model testing of particulate materials and geomaterials. So we have the usual Triaxial, odometric, simple shear, hollow cylinder and resonant column devices. These are advanced soil element testing apparatus that can allow us to subject them to the complex loads associated with trafficking railways directly underneath the loads transmitted directly through the rail, through the sleepers and into the ballast below. We also have resonant column devices from which we can understand the damping and the dynamic properties of soil, which are important. We're doing a big piece of work at the moment characterizing the backfill for a nuclear facility. Temperature controlled environments for gas hydrate generation testing, and we have a tank for ROV based seabed testing, which links in with our colleagues in maritime and maritime engineering. It's also staging for the fieldwork that we do, the sensor development, calibration, instrumentation, preparation. And so the field is also very much part of the laboratory, and the laboratory is an extension of the field and the fieldwork that we do. Anne, if you could advance it, please. So this is, it also supports the teaching and the education. And we, as I said earlier, our facilities are generally school facilities, and they support teaching, research and enterprise activity in our large labs, and that sort of mixed economy allows our students to be taught within a research-led environment where they can see state-of-the-art machines being used to support real problems to support the development of our understanding and knowledge of infrastructure. On the right-hand side, there's our the machine that was bought for the ballast testing work, a very large triaxial machine, 300mm diameter, 600 millimeters tall, about 100 kilonewtons samples, so a lot of manhandling and careful preparation of those materials. But it's the scale which really gets you a deep insight into the behaviour of those materials. And this is a dynamic process, and this is a very large dynamic triaxial testing machine that's been built specifically for the ballast, and which we've adapted subsequently for looking at backfill associated with a reactor facility as part of the Sizewell development. If you could move on, please, Anne. So we mentioned the field. So this is rail corrugations, looking at the impact of that and the transmission of the dynamic load through the rail and sleeper system into the ballast. And then we can take the measurements of that and induce those in the test that we might want to do in the triaxial machine or in the actuators. We can subject ballast and rail system and rail sleeper interactions in our long-term testing and understand how ballast degrades over time, and link that to the number of loading cycles directly, and also link that to fundamental element testing of the ballast material in that large triaxial. Thank you, Anne. So the TSRL laboratory, that is our material testing lab, widely used for industry research and teaching, static, cyclic and high strain rate testing, advanced imaging, thermography and deformation, strain and stress mapping, using high-speed cameras amongst other techniques, non-destructive testing, ultrasonics and composite manufacturing, and a range of environmental chambers, and a range of scales of machines to sort of take from very small test coupons right up to large elements of structure subject to cyclic and fatigue testing. If you can move on, please, Anne. And this is just looking down through the lab. Again, open plan and throughput of teaching, research and enterprise, all in state-of-the-art facilities, all blacked out because of the requirements of understanding the deformation characteristics of the material under test, using a range of different advanced techniques. For more information on that, I've put the link there to the site that describes much better and the apparatus and the range of testing capability that exists in the TSRL. Moving on, Anne. And then the energy lab, the energy group are housed within the NIL, and they're very active in monitoring systems for buildings and the urban environment and understanding how we use energy. The image that you can see on the right-hand side is a thermal image of one of our buildings at the university, where it was very noticeable that windows would be left open and obviously wasted heat. The buildings are of an age when they were very energy inefficient, and they would get hot. People would open the windows and then they would not necessarily close them. So a system was used using thermal imaging to alert estates and alert the building users of this, and so the buildings could be then properly managed. And a lot of this is all about people's behaviour and how we can do things to intervene and change people's behaviour in terms of energy economies. So demand modelling, infrastructure resilience, energy studies in cities, photovoltaics, marine energy systems, wind energy, and energy for development using PV systems in rural locations. All of those are very active areas of the energy group who are housed and support the activities within the UKCRIC National Infrastructure Lab. And I think that could be it. So access to the NIL. So access arrangements are being developed for the various facilities. Some of the facilities are still becoming fully operational, as I've mentioned a number of times. But we have a link to the UKCRIC site where there is a process of working up with the contact person at each of the UKCRIC laboratories in order for the laboratory to understand what's being proposed and whether it's possible to do the work within the laboratory, whether it has the capability primarily, and then a process by which the project should be more fully developed and integrated into a research council grant, if that's the route, which would link to the GES online application system, which would link to then the track costs associated with the facility, which is derived for each of these facilities, not just at all the UKCRIC facilities, which would form part of the process of costing up the proposed research in order to then get access into the laboratory. So it's an open process that is a tried and tested process of laboratory access for other national facilities, such as the National Wind Tunnel facilities. And also at Southampton, they're now currently developing the material imaging facilities, which will have a similar access arrangement, it being a national facility. So these are methodologies for getting access and linking in with the building and lab operators in order to facilitate that access. And as I said, we're just working up the finer detail of those access arrangements as these facilities become much more fully online and supportive then of external use of these national facilities. Okay, Anne. Thank you.